symmetry turns out to be a really important part of understanding signal structure. And so it's important to kind of define what we mean by symmetry for signals. And so right now we're going to talk about even and odd symmetry. So we want to know how to tell whether a signal is even or odd, or neither even nor odd, and be able to calculate the even and odd parts of a signal. So symmetry is really important, as I said before, and you can think of these symmetries as both algebraic and a graphical representation. They're sort of two ways of looking at the same property, and they're important for both continuous time and discrete time. So we have even signals, which look like if you flip them along the y-axis, they are the same. Odd signals, if you rotate them around by 180 degrees, they look the same. And then you have ones which are kind of in between, don't look even or odd. So signal is even algebraically if x of t is equal to x of minus t. So if we flip the time axis on the graph, then the signal looks the same. Or you can flip, say you're flipping it around the y-axis. So you get back the same signal. So it has kind of this, it looks the same on the left and the right. So if you want to check if a signal is even, you just have to verify that that condition holds. And it's the same thing for discrete time. X of n is equal to x of minus n. The signal is odd if x of t is equal to minus x of minus t, which corresponds to it having this kind of rotational symmetry. So if I took the signal and rotated it by 180 degrees, I'd get back the same signal. So in particular, if we look at this one, if I rotate this signal by 180 degrees, then this point here goes to this point here, and like this point here goes to this point here, and you can see we'll get back the same signal. And the same thing holds for discrete time. So if you want to check if the signal is odd, you just check the formula. Okay, so all signals, it can be written as a sum of even and odd signals, which is really cool. So given a signal x of t or x of n, you can write down the even part and the odd part such that the original signal is the sum of its even and odd parts. And these are done pretty straightforwardly by saying x even of t is x of t plus x of minus t over 2, and x odd of t is x of t minus x minus t over 2. And similar sort of formulas hold in discrete time. And x of t is x even plus x odd, because you can see the minus t, x of minus t components cancel out when you do this. So we've seen constructions that look like this before, like rhyme with this, and so there are some relations, and we'll talk about those next. But first, let's do some problems. So first problem is, so given x of t is sine of t cosine of 2t, check whether it's even or odd or neither even nor odd. So remember, you just have to check the definition. So you plug in x of minus t. The sine of minus t turns into minus sine of t. The cosine minus 2t turns it into cosine 2t, because cosine is even. So we get minus x of t. We get minus sine of t cosine 2t, which is minus x of t. So this signal is actually odd. And if you plot it, you'll be able to see graphically that it is in fact odd. What about the unit step function in discrete time? X of n is equal to u of n. Well, if we plot it, and we can plot it here, so like here's u of n, little lollipops going along. It doesn't, if I flip it around the y-axis, it doesn't look the same, and if I rotate it, it doesn't look the same. So graphically, we can see that it's neither even nor odd. But algebraically, you would look to see if u of minus n, you'd want to show that u of minus n is not equal to u of n, and it's also not equal to minus u of n. So, you just have to show that algebraically, and you'd be done. Okay, so let's look at a example where you have to find the even and odd parts, and let's look at an example in particular where you have to do it graphically. So here's the signal, which is piecewise linear and constant, so we can write it as a sum of unit steps and unit ramp functions. We can use these formulas to compute the even and odd parts, so we could write it out algebraically. There's like 6 terms here, so we're going to get 12 terms when we compute the even part. And the odd part. So that seems really messy, and that's also not going to really tell us what's going on. So let's try and do it graphically. And here, these are, when we talked about unit steps and ramps, we can describe these functions in terms of these steps and ramps. So that's something you should be able to do. Okay, so let's look at this function a little bit more closely. Looks nice, friendly looking function. So if we have x of t, what we need to do is first compute x of minus t. So here's x of t and x minus t. So this one is in red and this one is in blue. And we can just plot them both on the same plot. So now we get something that looks, we can see we've just flipped it over, flipped the x-axis, the time axis around to get the red plot. So now we just have to add these two together, or take the difference of these two to get the even and odd part. So let's start with the even. So we have the sum of these, we have these two signals plotted here. If we add them up, then we get this signal on the right here. So you can see that this little component here, for example, turned into this little spike over here because this part here is a +2 and a -1, so it gets canceled out. And it's an even signal, so actually we only have to draw the positive time axis part of it, and the negative time axis is just the mirror reverse of that. Okay, so then we just take, now we have the sum of these two, we divide by 2, and we get the even part of the signal. So it looks like this, and then we can write this down in terms of steps and ramps if we want to get a sort of more simplified expression. It's still going to be pretty messy in terms of the algebra. What about the odd part? We start again from the superposition of these two signals, and then we subtract them instead. We subtract the red signal from the blue signal. So if I subtract -1 from 2, so -1 from 2, I'm going to get 3 up here, and so on and so forth. You can see exactly how each of these little segments works out when you take the difference. And the important part again is that we know that this is going to be an odd signal, so we just have to figure out what's happening for positive time, and then negative time we can do it by doing this rotation around. So here we go. Here's our difference, and then we just have to divide by 2 again to get back our odd signal, x odd of t. So there we have it. So here's our x even and our x odd, and you can see they're even and they're odd, and if you want, you can add them up together to verify that we get back our original signal, and then you've turned the full circle in solving this problem. So of course you should try this yourself, finding the even and odd parts. We've seen many examples of signals in the previous videos in this class. So just take any one of those or make up your own signal and then check whether or not it's even or odd or neither even nor odd. And if it's in the third category, try to compute or graph the even and odd parts so that you get a sense of how this even-odd symmetry works. So this is one type of symmetry. For complex signals, we'll see another type of symmetry, which we'll discuss next.